Hey, Harsh here. If you've ever tackled with application latency, you know the bottleneck is really the core, it's I/O. The difference between a system that scales and one that crashes, there are a lot of concepts, but one of them is database indexing. But today, I'm not just gonna tell you that, okay, just index your weight loss. I'm gonna teach you a little more about what really indexing is. This video is about the complete theory and practice of data optimization. Let's start with the physics of data retrieval. Without an index, a database performs a full table scan. It reads every block sequentially from start to finish to find a match. That is an ON operation, linear complexity. If you double the data, you double the search time. An index creates a separate data structure that stores a specific column value alongside a physical pointer to the row's location on the disk. By sorting this structure, we convert that search from a linear scan to a tree traversal, which is O of log n complexity. In practical terms, searching a million rows might take a million operations without an index, but only 20 operations with one. The standard structure for indexing is B trees or balanced trees. Is the default in Postgres, SQL Server, and MySQL for a reason. It's optimized for disk storage. The balanced aspect is critical. It ensures that every leaf node is at exactly the same depth from the root. This guarantees consistent performance regardless of which key you are looking for. The tree is split into two types of nodes. Internal nodes, these contain the key ranges and the pointers guiding the engine to the correct child node. And leaf nodes, these contain the actual indexed values and the pointers to the full data row. This structure allows for efficient equality lookups and crucially, efficient range scans, for example, like finding dates between X and Y. Indexing is not magic, it's a trade off. You are trading write latency for read speed. Every time you insert, update, or delete a row in the main table, the database engine must also update every single index associated with that table. If you have a table with one clustered index and five non clustered index, a single write operation effectively becomes six writes. Furthermore, indexes consume significant disk space and memory. In write heavy workloads like log ingestion systems, over indexing will cause log contention and throttle your throughput. Index solely based on read necessity. In the context of InnoDB or SQL Server, you might understand the difference between clustered and non clustered. A clustered index isn't just a copy of data, it is the data. It dictates the physical storage order of the rows on the disk. Because you can only sort the physical data one way, you can only have one clustered index per table, usually the primary key. A non clustered index is a separate secondary structure. Its leaf nodes contain the indexed value and a locator, either the physical row ID or the clustered index key pointing back to the main table. This separation is why non-clustered index incur a lookup cost to retrieve full row data. When selecting columns to index, follow these three rules. Use its patterns. Target columns used in where filters, join predicates, and order by clauses. Cardinality. This is the measure of uniqueness. Columns with high cardinality, like email or UUIDs, make excellent index because they filter out massive percentage of rows. Low cardinality columns like gender or is active boolean are poor candidates. The optimizer may ignore them entirely in the favor of a full scan. Key size. Keep index keys small. An integer is faster to compare and it takes less spacing than a string. Smaller keys mean more data fits on a single memory page, reducing disk I/O. Single column indexes are simple, but real world queries often filter on multiple attributes. This is where composite indexes come in. The most critical concept here is leftmost prefix rule. A B tree on columns A, B, C is sorted by A, then B, then C. If your query filters by A or A and B, the index works. If you query only B, the index is useless because the data isn't globally sorted by B. Therefore, you always order your composite index columns by selectivity. Place the column that eliminates the most rows at the very beginning of the index definition. This is the holy grail of optimization, the covering index. Standard non-cluster indexes require a two-step process. Find the key in the index and look up the rest of the data in the main table. The second step is called a key lookup, and it is expensive. A covering index includes all columns required by query, both the filter columns and the selected columns. Because the index has everything the query asks for, the engine never touches the main table. In SQL Server, you use include clause to attach non-key attributes to the leaf nodes purely for retrieval purposes, keeping the sorting key efficient while eliminating lookups. While B trees cover 90% of use cases, specific workloads require specialized structures. Hash indexes, available in memory engines, they offer of-one lookups. They are instant for exact matches but useless for ranges or sorting. Bitmap indexes, used in data warehousing. They work well for low cardinality data like status or by using bit arrays, but they cause severe locking issues in transactional environments. Full text indexes, essential for large text fields. They use tokenization and stemming, finding ran when searching for run, which a standard like operator cannot do efficiently. A common pitfall is querying a modified column like where lower email equal to value. A standard index on email will be ignored here because the values in the index are a mixed case and not lowercase. Functional indexes or expression indexes allow you to index the result of a function. By creating an index specifically on lower email, the database stores the pre-computed lowercase values, allowing the optimizer to use index for case-insensitive searches. This bridges the gap between application logic and database storage. You can build perfect indexes and ruin them with bad queries. These are the common index killers. Function wrapping. Applying math or functions to a column in where clause forces a calculation on every row, a table scan. Leading wildcards. A query like percentage term prevents the B tree traversal because the starting of the string is unknown. Implicit casting. Comparing a string column to an integer value forces the database to convert the data types on the fly, often bypassing the index entirely. Always match your data types. How do you verify your work? You must read the execution plan. This is the optimizer's decision log. When you run explain or show plan, you are looking for red flags, table scan / cluster index scan. This usually means no suitable index was found. And key lookup / RID lookup, this means an index was used, but the engine had to jump back to heap for data. If this cost is high, consider using covering index. Automation isn't a guessing game, it's about reading the plan and adjusting the structure to lower the query cost. Performance degrades over time due to fragmentation. External fragmentation happens when the logical order of the index doesn't match the physical order on the disk. This forces the disk head to jump around and read sequential data, killing I/O. Internal fragmentation occurs when index pages have too much empty space, wasting memory. You must schedule maintenance, use reorganized for light fragmentation, and rebuild for heavy fragmentation, which may lock the table to restore the physical order of the data. Implementation is done via create index command. Be specific. Use unique to enforce data integrity constants at database level. For composite indexes, remember the order on table column A, column B. You can also specify sort direction like order date descend. If your application shows the last orders first, a descending index matches the query's sort order perfectly, saving the database from having to resort the results. For example, in e-commerce scenario, we have a product catalog that is read heavy with millions using filtering and searching. Clustered index on product ID for fast retrieval by ID, composite index on category ID, price, and rating. We put up the category first because it is the most common filter, and covering index for the listing page. We create an index on price that includes product name and image URL. This means when a user filters by price, the database retrieves the name and the image directly from the index leaf nodes. It never touches the heavy product table. This is how you achieve some millisecond latency at scale. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.